Hey Calculus class! Today you're going to learn topic 36, the Fundamental Theorem of Calculus part 2. Alright, so we're going to do a little investigation. I want you to let capital F of x equal the integral from 0 to x of little f of t dt. You're going to complete the table by calculating the area under the function. Okay? So then once you're done with that, then we're going to look at when is f of x increasing and decreasing, and what is the algebraic equation for little f and big F. So looking at this graph of little f is actually this horizontal line right here at 3. Okay? So in order for me to calculate the integral from 0 to x, well, the x value is going to change each time. So the first time I'm going to go from 0 to -2. So what that means is that I'm going to start here at 0, trying to draw a rectangle on a computer is not easy, and then I'm going to go to -2, and I want to find the area underneath the curve between those intervals. Well, I just have a rectangle, so my base is 2, my height is 3. So that means that my area of that is -6. And the reason why it's -6 is because the change is from 0 to -2. Now I'm going to go from 0 to -1. So to do that, I'm going to do the rectangle from 0 to -1. That times the base is 1, the height is 3, and since it's going from 0 to -1, I have to change it to negative, so I get an area of -3. Now I'm going to go from 0 to 0. Well, we know that property that you can't find the area at just one point, so the area underneath that is 0. Then we're going to do it from 0 to 1. Well, from 0 to 1, I have a base of 1, a height of 3. So that gives me an area of 3. Then I'm going to keep going. From 0 to 2, so base of 2, height of 3. Gives me an area of 6. From 0 to 3, base of 3, height of 3, so an area of 9. And from 0 to 4, a base of 4, height of 3, so an area of 12. So in order to determine when big F is increasing or decreasing, if you can remember back from Unit 3, we know that a function increases when its derivative is positive. So since we are finding the area underneath little f to get big F, that means that the derivative of big F is little f. And since little f is basically a horizontal line at +3, that means that big F is increasing on the entire interval, -infinity to infinity, because little f of t is positive. Now, what is the algebraic equation for f of t and big F of x? Well, little f of t, that's just a horizontal line. And the equation of a horizontal line is always y equals whatever number. So that equation is just f of t equals 3. Now, to get the equation of f of x, right, we could, if you wanted to, you know that a horizontal line, right, its antiderivative is going to be a diagonal line, or y equals mx plus b. Well, we can find the slope of that line, right, which is just going to be 3, because the derivative of a line is its rate, which is its slope. So the equation of my line is 3x, and the plus b is 0 because the y-intercept is 0. All right, I want you to see if you can do this one on your own from start to finish. And this time, the function f is this horizontal right here at -2. And this time you are taking the integral from 2 to whatever the x value is. All right, let's see how you did. From 2 to -2, you should have gotten an area of 8. From 2 to -1, you should have gotten an area of 6. From 2 to 0, you should have got an area of 4. From 2 to 1, an area of 2. From 2 to 2, you should have gotten 0. From 2 to 3, you should have gotten negative 2. And from 2 to 4, negative 4. Now, when is big F of x increasing or decreasing? In this case, big F of x is decreasing on the entire interval, negative infinity to infinity, because this time little f of t is negative. The algebraic equation that you should have gotten for little f is negative 2, and for big F, negative 2x plus 4. And the plus 4 is your y-intercept. So 0, 4 is your y-intercept, so hence the plus 4. All right, now I want you to see if you can do this one. So this one, this time, at little f of t is a diagonal line. So you're going to probably have to find the area of shapes that are not rectangles necessarily. And that you're going to go from 0 to x. So I want you to complete the table by calculating the area underneath this function. Then you're going to determine when big F is increasing or decreasing. Then you're going to plot the points x comma f of big F of x, so this table, on the grid provided. And then you're going to see if you can see a relationship between little f and big F. Let's see how we did on the graph for the table. Should have gotten from 0 to negative 1, negative 5. 0 to 0 is 0. 0 to 1, 3. 0 to 2, 4. 0 to 3, 3. 0 to 4, 0. And 0 to 5, negative 5. When is big F of x increasing and when is it decreasing? You should have said that big F of x is increasing on the interval from negative infinity to 2 because little f is positive, and decreasing from 2 to infinity because little f is negative. And you can see that right here in the graph. Now, if you plotted the points correctly from this table, you should get that big F is a parabola or upside down parabola. And the relationship between little f and big F is that the derivative of big F equals little f. All right, now let's look at some more. This time, for each part, for part A and for part B, I've given you two little functions for little f. You're going to first evaluate the integral from 0 to x to find big F. And it will be in terms of x. Then I want you to take the derivative of big F. So I'm going to set up my first integral for part A. So that means I'm going to go from 0 to x of t cubed dt. I'm going to find the antiderivative of t cubed, which is t to the 4th over 4. I'm going to evaluate it from 0 to x. When I do that, I'm going to get x to the 4th over 4 minus 0 to the 4th over 4, which just gives me x to the 4th over 4. So that's big F. So that's big F. Now the directions say, now take the derivative of big F. So now when I take the derivative of x to the 4th over 4, I'm going to get x cubed. All right, I want you now to see if you can do part B on your own. All right, let's see how we did. So the first thing is to set up the integral from 0 to x of sine t dt. Take the antiderivative of sine t, which is negative cosine. You're going to evaluate from 0 to x. When you do that, you get negative cosine x plus cosine 0. And we know that cosine of 0 is 1. So this is big F of x. Now I'm going to take the derivative of this. When you take the derivative of this, you get sine of x. Now, is there anything that you notice about the derivative of big F? Well, hopefully you noticed that the derivative of big F is little f. It's just in terms of x instead of t. All right, now let's go ahead and try these ones. So first thing is you're going to find the antiderivative. Then you're going to evaluate from 1 in part A, in this case, from 1 to x squared, and in part B, 1 to 5x squared. So I want you to see if you can do it on your own first. All right, let's see how we did. So I already know that the antiderivative of t cubed is t to the 4th over 4. Now I'm going to evaluate from 1 to x squared. So when I do that, I get the following. And for the purpose of this, I'm going to not simplify this x squared to the 4th. And you'll see why in a minute. So now I'm going to go ahead and take the derivative of this. When I do that, I have the chain rule. So the derivative of x squared is 2x. And the derivative of the outside to the 4th is 4 times the inside cubed, all over 4. And then the derivative of a constant is just a constant. Now I'm going to simplify it just to this point, and you'll see in a minute why I stopped there. All right, for part B, you know the antiderivative of sine t is negative cosine t. Evaluate from 1 to 5x squared. And cosine of 1 is just some number, so I'm just going to leave it as cosine 1. Now I'm going to take the derivative. When I take the derivative of this, for the first term, I have to use the chain rule. So derivative of the outside is negative sign, so that means the negatives cancel. And I leave the inside alone, times the derivative of the inside, so the derivative of 5x squared is 10x. And then the derivative of just a constant is 0. Now, the reason why I left these functions not completely simplified, especially this one, I guess technically this one is simplified, is to look at this for part C. What do you notice this time about the derivative of big F? What you should have noticed is that the derivative of big F is still little f in terms of the upper limit. So notice here the upper limit's x squared. My little f is t cubed. Here is the upper limit cubed. Same here. Here's little f, sine t, upper limit is 5x squared. Here I have sine of the upper limit times the derivative of the upper limit. So the derivative of x squared is 2x. The derivative of 5x squared is 10x. And that comes from because when you took the derivative of big F, you had to use the chain rule. So this leads us into the Fundamental Theorem of Calculus Part 2, or short version, FTC2. If little f is continuous on a to b, then the function big F is defined by capital F of x is equal to the integral from a to x of little f of t dt, where x is between a and b, is continuous on a to b and differentiable on a to b. And we can say that the derivative of big F is equal to little f in terms of x, or you can think about it as when you are asked to find the derivative of the integral, that is just the function inside in terms of x. And I want you to keep in mind that your book calls this part 1. Now, for the second part I had you do, where you had to do the chain rule, what this one looks like, it's still the Fundamental Theorem of Calculus Part 2, but this time, notice here in my limits, I have a to some, my upper limit is some function in terms of x, not just x. So this time, when I want to find the derivative of big F, or the derivative of the integral, that means I'm going to have my original function, the little f, in terms of the upper limit, so in terms of g of x, times the derivative of the upper limit. Note this looks pretty similar to the chain rule. Or another way that you can think about it is derivative of the integral will give you the following. And another little note, in order for this to work, for this theorem to work, the constant must always be the lower limit. So there might be some times where you'll have x on the bottom and a on top. That means you're going to have to multiply by negative to flip the limits. Okay, so here is what it would look like. All right, so let's go ahead and do an example. So if big F is equal to the integral from pi over 2 to x of tangent inverse t dt, find f prime of pi over 6. So you don't actually have to do what I had you do earlier, integrate and then differentiate. You can skip that step because we now know by the Fundamental Theorem of Calculus Part 2 is that the derivative of an integral is just going to be the function itself in terms of the upper limit, in this case x. So that means that the derivative of big F is just tangent inverse in terms of x. Now in order to find the derivative of big F in terms of pi over 6, is I'm just going to plug in pi over 6, and tangent inverse of pi over 6 is 0.4823. That's fine if you plugged it in your calculator, or you could have done the unit circle as well. All right, now I want you to go ahead and see if you can do number 2 on your own. Let's see how you did. All you had to do was just find the derivative of f, so the derivative of the integral. So all you're doing is wherever you see a t, you're replacing with an x, and you're done. All right, now let's try this one. This one is a little bit different because you have an upper limit that's not just x. So you remember that your original you're going to replace the inside still with the upper limit, so you're going to replace r with x squared. But this time you do have to multiply by the derivative of the upper limit. And when you simplify, you would get the following. All right, and let's try this one. Find dy dx, so find the derivative of y if y equals the integral from sine x to cosine x of 1 minus 1/2 t dt. Notice that the lower limit is definitely not a constant, and neither is the upper limit. So what you actually have to do for this one is you have to split this integral up by choosing a constant that would be inside an interval of sine and cosine. And that x value is actually 0. So that means I can split this up from sine to 0 plus 0 to cosine. Then for this first one, I need to make sure that the 0 is on the bottom, is the bottom limit. So that means I'm going to have to multiply this first integral only by a negative. Now I can go ahead and apply the Fundamental Theorem of Calculus Part 2. So in the first integral, wherever I see a t, I'm going to replace that with sine x. In the second integral, anywhere I see a t, I'm going to replace that with cosine x. But since the upper limit is not just an x, I'm also going to have to multiply each one by the derivative of the upper limit. So that means for the first one, I replace the t with sine x times the derivative of sine x plus the function in terms of cosine x times the derivative of cosine x. And once I actually take the derivative of the sine and the cosine, I get the following. And you can simplify this even more. So I distributed this negative through. I also distributed the cosine through. Here I distributed the negative sine through. And you can even simplify this even more by combining like terms. So you have the 1/2 sine x plus the 1/2 sine x, which gives us just 1 sine x. Then you have a negative cosine and a negative sine. All right, now we're going to look at a very, very common AP open-ended question. I would be surprised if a question like this would be not on the open-ended. It usually is every year. So for this question, you're going to let big F of x equal the integral from 2 to x of little f of t dt. The graph of little f on the interval from -2 to 6 consists of 2 line segments and a quarter of a circle. And as you can see it in the picture. There's your line segment, there's your second line segment, and here's your quarter circle. And this is the graph of little f. For part A, find big F of x, find big F of 0 and big F of 4. So for F of 0, that means I'm putting 0 in for x, just like we did at the very beginning of this video. So that means I want to find the value of big F from 2 to 0, and since the order of the limits is out of whack, I'm going to have to multiply by a negative, so it's from 0 to 2. So when I look at my graph, here's 0, here's 2. And you should see that you have a triangular shape, and we can calculate the area of this triangle. We have a base of 2, a height of 2, and then of course divide by 2 for the area of a triangle, which will give me -2. Now I'm going to do the same thing for big F of 4. This time I'm going from 2 to 4. When I look on the graph, 2 to 4 is just that quarter circle. So I am finding the area of this quarter circle. So I'm going to use the equation pi r squared divided by 4, and the radius is 2. So when I set that up, I just get pi. For part B, you're going to determine the interval where big F of x is increasing, and you need to justify your answer. So we know that the original function increases when the derivative is positive. So that means we are looking for when little f is positive, and we should see that little f is above the x-axis from 0 to 6. So we say that big F is increasing when the derivative of big F is positive. And since the derivative of big F equals little f, and little f is positive on the interval from 0 to 6, then big F is increasing on 0 to 6. All right, for part C. Now we want to find the critical numbers of big F and determine if each corresponds to a local min, local max, or neither, and justify your answers. So keep in mind, this is the graph of your derivative. So we know that critical numbers exist where the derivative is 0. And this graph is 0 at x equals 0 and at x equals 4. Okay? Now we have to determine if each corresponds to a local min, max, or neither. Well, we know a local min occurs when the first derivative changes from negative to positive, and we know that a local max occurs when the first derivative changes from positive to negative. So when we look at x equals 0, you'll see that the graph of f, little f, which is the derivative, is changing from negative to positive. So that means at x equals 0, we have a local min. But when you look at x equals 4, the graph of the derivative stays positive. So that means at x equals 4, we have neither. So an acceptable answer would be at x equals 0, big F of x has a local minimum because the derivative of big F equals little f, and that changes from negative to positive. At x equals 4, big F of x has neither a local minimum nor a local maximum because the derivative of big F equals little f does not change sign. All right, for part D, find the absolute extreme values of big F and the x values at which they occur. Justify your answer. Well, we know that absolute extrema can occur at the endpoints or at any of the critical numbers. So that means we need to find the value of big F of x at the critical points and at the endpoints. Well, we already have big F of 0, and we know that x equals 0 is a critical point. That was from part A. We also found big F of 4, which was another critical point. That was also from part A. Now we just have to find the values of big F at the endpoints. So that means we need to find the value of big F at -2. In order to do that, we have to flip the limits so that the smaller value is on the bottom. So that means I'm going to take negative of the area underneath the curve from -2 to 2. And when you look at the graph, you'll notice that from 0 to -2 and from 0 to +2, you basically have the exact same triangle, just one's above the curve and one's above the x-axis and one's below the x-axis. And so since the one above the x-axis has positive area, the one below the x-axis has negative area, that means the area underneath the curve from -2 to 2 is 0. Now we need to find the value of big F at 6, so we're going to go from 2 to 6. To do that, we already have the value of the curve from 2 to 4, which was that quarter circle, which we know is pi. Now we just have to add on the area underneath the curve from 4 to 6, and that's just a triangle. So you have pi, which is the value from 0 to 4, plus 1/2 times the base, 2, times the height of the triangle, 4, which will give you pi over 4. So to determine which one is our lowest value, so your absolute min, that would be my lowest y value between these four x values, which is at -2. And then my largest y value, or my absolute maximum, will be my largest y value. Well, I know that pi is 3.14 so on, so it makes sense that if you add 4 to pi, that's going to be a bigger number. So that means that f of 6 equals pi plus 4 is my absolute maximum, and f of 0 equals -2 is the absolute minimum. And I just realized, I am sorry, I actually did not justify my answers. So you actually need to add a because. So the because for this one is that you could say two different things. You can either say that the value of big F of 6 is the largest value between the x values of the endpoints and the critical points, and then vice versa for the absolute minimum. For part E, I want us to find the x coordinates of the inflection points of big F of x and justify your answer. Right, so if you can remember from Unit 3, inflection points occur where the second derivative is equal to 0. But in terms of the graph of the first derivative, that means that that's where the first derivative has a horizontal tangent line. Now when you look at the graph of little f, you should see that there's a horizontal tangent line at x equals 2, but it's also where the second derivative does not exist. So where you cannot take the derivative of the first derivative, which is at x equals 4 because you have a corner. So we can say that big F of x has inflection points at x equals 2 and x equals 4 because big F double prime is equal to little f prime, and that's where it changes sign at those points. And that's an addition of, that's how I knew it's going to be either 2 or 4, where you have a horizontal or does not exist tangent line on f prime, or the first derivative. But then you know it's an inflection point because it has to change sign. Now determine the intervals where the graph of big F is concave down. Justify your answer. Well, we know concave down means that that is where the second derivative is negative. So that means on the graph of the derivative, that's where the tangent lines have negative slope. So we can say that big F of x is concave down on the interval from 2 to 4 because the derivative of big F equals little f is strictly decreasing on the interval, and f double prime is equal to little f prime is negative on the interval. Well, I hope you enjoyed learning about the second fundamental theorem of calculus, and I will see you in class tomorrow. Have a good night.